Today we're going to talk about material from Chapter 4. These are expressions, identities, and properties, and then we're also going to talk about exponents. So starting with our definitions, first definition is about expressions. A numerical expression is a combination of numbers, parentheses, and operation signs, which represent a single number. And an algebraic expression is a combination of numbers, parentheses, operation signs, and letters, which represent a number for some choice of numerical values for the letters. Look at some examples. And for each one, we're going to write numerical expression, algebraic expression, or not an expression. So you should fill this in on your handout as we go. And I'll try to pause and give you a chance to do that. So this first one, we have 32 times the quantity of 52 plus 7 minus 38 times 1/4. And that will be a numerical expression because there are only numbers, parentheses, operation signs involved. Next, we have 3 plus divided by 7. This is not an expression because it just doesn't make sense. A plus 3. This is an algebraic expression because if we had a value for a, we could find a single number. 5 pi plus 4. This is a numerical expression. Even though we may be less comfortable with pi, it is a number, and so this is a numerical expression. 3x plus 2 equals 7. This is not an expression, although it seems like it might, maybe it should be. It's an equation, which is different, and we'll talk about those in a few minutes. A plus b times a minus b. That's an algebraic expression. X, algebraic expression also. 12,307, numerical expression. 5 divided by 0. Although this appears like it should be a numerical expression, it is not, because to be a numerical expression, we have to be able to get one single numerical value for it, and we cannot here, because this is undefined. And similarly for y divided by 0, it appears to be an algebraic expression, but it is not defined, so it is not an expression. And just as a note, although we were making the distinction between numerical expressions and algebraic expressions, technically any number or numerical expression is also an algebraic expression. Now we're going to talk about evaluating expressions. An algebraic expression can be evaluated by assigning specific values to the letters appearing in it. The expression then becomes a number. So we're going to look at some examples, and we're going to evaluate by assigning the specific values given. So first expression, we have x plus 7. We're going to assign x the value of 4. So in our expression, we have x plus 7. We're going to replace the x with 4. So we get 4 plus 7, which is equal to 11. Next, we're going to look at x squared plus 3y. We're going to evaluate that with x equals 0 and y equal 1. So where we have x, we're going to replace it with 0, and where we have y, we're going to replace that with 1. So that's going to give us 0 squared plus 3 times 1, which gives us 0 plus 3, which is 3. And then finally, we have 2x over x plus y plus 4, and we're going to evaluate that at x equals 2 and y equals 3. So we're going to, again, replace x with 2 and y with 3. That's going to give us 2 times 3 in the numerator and 2 plus 3 plus 4 in the denominator, which is 12 over 9, which we can simplify to be 4 over 3. All right, now continuing with definitions. Our next definition is for an equation. An equation is a statement that two expressions are equal. And an algebraic identity is an equation that is true no matter what their numbers represent. For each of the following equations, we're going to do this example, label as an identity or not an identity. And I, again, will try and pause to give you a chance to figure it out. X plus y equal 1. This is not an identity because whether it's true or not depends on the values of x and y. Y equal 2x minus 3. Again, this is not an identity because it depends on the values of x and y. 2 times the quantity x plus 7 equal 2x plus 14. This is an identity because it is always true. And 9 times the quantity x minus 1 plus 15 equals 3x plus 4. This is not an identity because it depends on the values of x. Now, there are 3 types of identities. There are properties, which are basic identities. There are rules, which are simple and useful identities worth memorizing. And then there are identities, what we call identities, which are less frequently used, but always true. So, for some examples, arithmetic properties. For all whole numbers a, b, and c, the following properties, meaning basic identities, are true. So first one, commutative properties for both multiplication and addition, associative properties for multiplication and addition, the distributive property, and then the additive identity and multiplicative identity properties. And these are all properties we are already familiar with. We've talked about them before. Now we are going to think about a particular identity, the quantity a plus b squared equal to a squared plus 2ab plus b squared. And for a teaching sequence for this, we're going to look at the examples of 10 plus 7 quantity squared, a plus 1 quantity squared, and then a plus b quantity squared. So in this case, what we're doing is we're going from very concrete, where we have 2 numbers for each, to a little more abstract, where we have one variable letter and one number. And then also our last step is with 2 variables. Now for these, you should follow the links in the non-narrated slides to the YouTube videos I've posted, or follow the link for the playlist posted in Blackboard. Okay, we're also going to see the teaching sequence or a teaching sequence for the identity a plus b times a minus b equal a squared minus b squared. So the first example, we're going to look at 10 plus 3 times 10 minus 3. So this is a very concrete example again. And then a plus 1 times a minus 1, again, abstract with the a, concrete with the 1. And then finally, full generality, a plus b, a minus b, so abstract for both of them. And here also you should pause and go watch the videos that are posted in YouTube. Again, in the non-narrated slides, you can just click the links and get there, or you can get that from the link posted in Blackboard. All right, and then the identity a plus b times c plus d. We're going to draw a rectangular array to illustrate this, and from that, we are going to get the identity itself, which you'll see at the end of the video, which again, can follow the link in the non-narrated slides or the link posted in Blackboard. All right, a number line interpretation for this identity a plus b times a minus b, which allows us to do some mental math with it. I did this one with a pen cast. We'll see how you like it. I'm not sure it was quite as good as the videos. But if you follow the link, that will take you to Blackboard, where the link for the pen cast is given, and you're going to have to log into Blackboard when you follow that link from the non-narrated slides. But it's going to tell us how we can interpret a plus b times a minus b in terms of mental math, which will allow us to do some multiplication problems maybe a little more simply. All right, now we are moving on to talking about exponents. And first we have our definition that a to the m, so we have a to the m, is equal to a times as many times as we need to have m times. So the number a is called the base, and m is the exponent or the power. And for example, if we have 4 to the 3rd power, 4 is our base, 3 is our exponent, and that is equal to 4 times 4 times 4. Okay. So now we're going to talk about a rule, and we're going to look at a teaching sequence for this rule. So remember, when we were talking about the 3 types of identities, one type was a rule. So that is something that is simple and worth memorizing, so that it simplifies calculation for us, is really what it's here to do. So in our teaching sequence, again, we are going to go from concrete to more abstract. So we're going to start with 10 to the third times 10 to the fifth, and you should fill things in on your handout as we're going. So when we have 10 to the third times 10 to the fifth, that's going to be 10 times 10 times 10, 3 times there for 10 to the third, and then 10 times 10 times 10 times 10 times 10, 5 times there for 10 to the fifth. And so that is equal to 10 times 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 10. Aren't you glad I chose the relatively small numbers of 3 and 5 here? And that will be equal to 10 to the 3 plus 5. Now, I know you're thinking, oh, that's 10 to the 8th power, and you are right. But we're writing it this way to emphasize what's happening with the rule, because we're trying to understand why this rule works. All right, next, we're going to increase our abstraction just a little. We're working with 10 to the third still, but now 10 to the m. So we're going to have 10 times 10 times 10. That's from 10 to the third. And then we have 10 times 10 times 10, however many m times actually is. So when we put all of those together and count the number of tens we have, we're going to have 10 to the 3 from our 3 here, plus m from the m tens we get here. All right, now going back and increasing our abstraction again, but notice we've abstracted in the base. I'm using an x here instead of a 10, but we've gone back to concrete values for the exponents again. So we'll get x times x times x. This is from x to the third, and then x times x times x times x times x, and that is from our x to the fifth. And that gives us x times 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 x. Again, glad we chose relatively small numbers for 3 and 5. And that will be equal to x to the 3 plus 5, which again is equal to 8. We know that, but we're trying to emphasize how the rule works going from our x to the third times x to the fifth to x to the 3 plus 5. A little bit more abstraction here. We have a, so an abstract base to the third, a concrete number for our power, times a to the m, again, abstract base, but notice same base in either case, and an abstract number for the power. So this will be a times a times a, that's from our a to the third, times a, however many times we need for m. And then how many a's does it give us being multiplied together? That is a to the 3 plus m, again, the 3 from here, the m from here. And then our final abstraction step here, we have a to the n times a to the m, which will be equal to a to the n plus m. Okay, rule 2. So here we have a to the m divided by a to the n is equal to a to the m minus n. And we're actually making an additional assumption here that m and n are whole numbers, and in this case that m is greater than or equal to 0. So we have more powers of m in the numerator than the denominator, and we're going to assume a is not 0 because we can't divide by 0. We don't want any zeros in the denominator. So we're going to start with a concrete example, 2 to the 7th over 2 to the 3rd. So again, starting very concrete, just with working with numbers. So 2 to the 7th in the numerator, that's going to be 2 times 2 times 2 times 2 times 2 times 2 times 2, 7 times, divided by 2 times 2 times 2, 3 times. And then what we're going to notice is that we can cancel the 2's that are in common in the numerator and denominator. So notice we've done that here. And now that leaves us only with 2 times 2 times 2 times 2 in the numerator, but that's 2 to the 7 minus 3, because we started out with 7 in the numerator, and then we canceled them with the 3 2's that were also in the denominator. Again, notice that we're writing this as 7 minus 3 rather than 4, so that we can emphasize the connection with our rule. All right, now we're going to continue with our abstraction, and here we have m as the exponent in the numerator, and m we're assuming is greater than or equal to 3. So 2 to the m, that's 2 times 2 times 2, m times. And 2 to the 3rd, again, that's 2 times 2 times 2, just the 3 times. And we're going to cancel the things that we have in common between the numerator and denominator. And notice, of course, that leaves us still with some 2's in the numerator. Well, how many of them will there be? We started out with m 2's in the numerator, and then we got rid of 3 of them from the denominator. So we're left with 2 to the m minus 3. Okay, now continuing, we are abstracting a little bit more with x to the 7th and x to the 3rd, but again, our powers are concrete. So that gives us 7 x's multiplied together in the numerator and 3 x's multiplied together in the denominator, not to be confused with 7x and 3x, but we're multiplying them all together. We're going to cancel the x's we have in common between the numerator and denominator, and then what we're going to have left is the number of x's. So we started out with 7 in the numerator, we canceled with 3 of them in the denominator, so it leaves us with x to the 7 minus 3. Again, making that connection to what the rule says rather than writing x to the 4th. Now continuing our abstraction, I had to go to a different slide because I was out of space. So now we're going to have something more abstract in the base. So a is our abstract unknown thing. M is an abstract exponent as well, but still has something concrete with the 3 in the base. So a to the m, that's a multiplied by itself m times. So we have m a's we are multiplying together in the numerator. We have 3 a's we are multiplying together in the denominator. We are going to cancel the ones that are in common between numerator and denominator. And then we need to figure out how many a's are left. Well, we started out with m. We got rid of 3 of them. So we have a to the m minus 3. And finally, that leaves us with our rule, a to the m over a to the n, and we're going to end up with a to the m minus n, which is our rule 2 when we're finished. Okay, in the home stretch, almost. Got a few more things to do here, but we'll make it. Okay, rule 3. This is a to the m raised to the n equal to a to the mn, where m and n are whole numbers. And we're going to look at this teaching sequence. You should fill in again as we go. Some of these you already have filled in on your handout, but this way you can watch as I go. We're going to start with the most concrete example possible that we can do here, where we're just using numbers for a, m, and n. So 2 to the 4th raised to the 3rd power is going to give us 2 to the 4th times 2 to the 4th times 2 to the 4th. That's from our definition of the exponent. And that's what we're going to have all the way through this first column. That is what we're using. Then, according to rule 1, when we're multiplying together with the same base, we add the exponents. So this will be 2 to the 4 plus 4 plus 4. And then from our definition of multiplication, 4 plus 4 plus 4 is 4 times 3. And so notice we went from 2 to the 4th raised to the 3rd power to 2 to the 4 times 3. Again, we know that's 2 to the 12th power, but we want to emphasize the connection to the rule here because we're trying to teach the rule. All right, then x cubed squared. Again, increasing the abstraction here, I changed the base to be a variable instead of a number. X cubed squared gives us x cubed times x cubed from the definition of the exponent. Using rule 1, that's going to be x to the 3 plus 3. And then from the definition of multiplication, that will be x to the 3 times 2. Emphasizing the format for the rule again. In our next line, we have x to the 3rd raised to the 4th power. So using the definition of the exponent, it's going to give us x to the 3rd times x to the 3rd times x to the 3rd times x to the 3rd. From rule 1, we can convert that to x to the 3 plus 3 plus 3 plus 3. And then from our definition of multiplication, that gives us x to the 3 times 4. All right. Now, moving on to our next line, the abstraction increasing here in the exponent, but we still have something concrete with the 3 there. So we have x cubed times x cubed times x cubed, so on, times x cubed, and we multiply x cubed by itself n times. Now using rule 1, that means we're going to have x to the 3 plus 3 plus 3 plus 3 and so on. And there are n of those 3's in the exponent this time. Now using the definition of multiplication, that means we're going to have x to the 3 times n. All right, most general. Basically, our rule 3 here, we have x to the m to the n. And what we're going to get here, we have x to the m times x to the m. We're going to multiply that together. So all of these times, n x to the m's. So that's going to be x to the m plus m, and so on, n times. And then using our definition of multiplication, that's going to be x to the m times n. All right, rule 4. So this is the first rule where we're changing the base. We have a to the m times b to the m is equal to the quantity ab to the m. But notice the exponent stays the same. And again, follow along and fill in on your handout. Some of this you've already got, but fill in as we go. So first, we have 2 to the third times 5 to the third, which we can rewrite as 2 times 2 times 2 times 5 times 5 times 5, using the definition of exponent for both 2 to the third and 5 to the third. And then we're going to use the any order property to reorder our multiplication there so that we have 2 times 5 times 2 times 5 times 2 times 5. So we're just pairing 2's and 5's together. And then from our definition of exponent again, we have 2 times 5 multiplied 3 times. So that's 2 times 5 quantity to the third power. Moving on to a little bit of abstraction here, we have 5 to the third times y to the third. So that's 5 times 5 times 5 times y times y times y. And then using the any order property again, we get 5y times 5y times 5y, which from the definition of exponent is going to give us 5y to the third power. Increasing our abstraction now with x to the fourth and y to the fourth, but still keeping those concrete powers. We're going to have x times x times x times x from the x to the fourth, y times y times y times y from the y to the fourth. Using the any order property, that will be xy times xy times xy times xy. And then using the definition of the exponent, that will be xy to the fourth power. And then finally, our rule, most general way we can form this, we have x times x multiplying x together n times, y together n times. Using the any order property, we're going to get xy times xy and so forth, x times xy, and that will be n times. And then our definition of the exponent tells us that will be xy to the n power. Okay. And finally, we get to our last examples. And, this video is only going to be about, maybe less than 30 minutes, but I really miss being in the classroom with you guys. I wish we were. Okay, we're going to simplify the following expressions. I'm going to do it one particular way because I don't have you guys here to tell me, oh, let's try this. So we're just going to have to follow along. And as we go, I chose one particular way to do this. There are many other ways we could have done this. Okay, first thing I'm going to do, 15 to the fifth over 5 to the fourth. I'm going to rewrite that 15 as 5 times 3. And then using rule 4, which we just talked about, that's going to be 5 to the fifth times 3 to the fifth divided by 5 to the fourth. And then that gives us 5 to the 5 minus 4. That's using rule 2, I think, times 3 to the fifth. So that we can rewrite as 5 times 3 to the fifth. And I'm just going to leave it in that format. Now, our next example, we have something much more complicated on number 2. We have 15 to the fourth times 45 to the third times 35 squared over 5 to the third, 9 squared times 15 times 21. And again, I just picked one way to simplify. You could do it another way. As long as you get the same answer at the end, it's fine. I'm going to change the 15 to 5 times 3, the 45 to 5 times 9, the 35 to 5 times 7. In the denominator, the 15, I'm changing to 3 times 5, and the 21 to 3 times 7. Next, I'm going to use Rule 4 and rewrite this as 5 to the 4th times 3 to the 4th times 5 to the 3rd times 9 to the 3rd times 5 to the 3rd times 7 to the 3rd in the numerator. And then I'm also using Rule 1 in the denominator to get 5 to the 3rd, 9 squared, 5 times 3 squared times 7. Now some of you might be saying, why didn't you multiply out the 9 as 3 times 3? I did not, because in the numerator we could get a 9 out of the 45 as well. Now we are going to cancel the things that we can cancel. And so we see this 5 to the 3rd in the denominator. I'm going to cancel with the 5 to the 3rd in the numerator. The 9 squared in the denominator, we're going to use Rule 2, I think it was. So the 9 squared, we're going to cancel with the 9 to the 3rd, and that's going to leave us with 3 minus 2, or 1. The 5, the next 5 in the denominator, we're going to use Rule 2, again, I think it was. We're going to cancel with the 5 to the 4th in the numerator. So 4 minus 1 will give us 3. The 3 squared, we're going to cancel with the 3 to the 4th in the numerator. And again, we're using Rule 2, so that's going to be 4 minus 2 gives us 2. And then the 7 I'm going to cancel with the 7 to the 3rd, so that's going to give us 3 minus 1 is 2. So now all together we are left with 5 to the 3rd times 3 squared times 9 times 5 to the 3rd times 7 squared, which, noticing we've got 2 5 terms in there, we can combine those to get 5 to the 6th times 3 squared. And now I'm going to change the 9 into 3 times 3, which is 3 squared, times 7 squared. And then I'm going to reorder just because I like the lower numbers first. We get 3 to the 4th times 5 to the 6th times 7 squared. And finally, x to the 6th times xy to the 4th over x to the 4th times y squared. And I'm going to use our last rule, Rule 4 first. That gives us x to the 6th times x to the 4th times y to the 4th. Now we're going to cancel the things that will cancel. The x to the 4th and the x to the 4th from the numerator and denominator will cancel. And then the y squared, we can cancel with the y to the 4th, and we're going to be left with 4 minus 2, which is 2 in the numerator for the power. And we'll get x to the 6th times y squared. And that's it.